So in this section, this is section 8.1, and it's very short. The idea behind section 8.1 is we're just defining what a network or a graph is. So we've actually already seen this, but let's go ahead and define one. You may have seen graphs before in other classes. For example, graph theory, that's where you work with graphs. And so here's a graph, and notice the pieces that it consists of are the circles, which are called vertices or nodes. So it's a vertex or a node of the graph. And then also these line segments are called edges or arcs. Okay, so depending on which branch of mathematics you're in may depend on what you're going to call it, but either way, so the way we actually define a graph, let me label this to make it more specific here. Let's see, 1, 2, 3, 4, 5. This is called an undirected graph because the edges don't have a direction. Undirected graph. Okay, what we're going to be doing is working with directed graphs most of the time. So we're going to look at a directed graph in just a second, but let's go ahead and look at our undirected graph first. So our undirected graph is defined by our set of vertices. So let's go ahead and set our vertice set to be 1, 2, 3, 4, 5. Okay, and then we also have an edge set. So we'll call that E. And what does that consist of? That consists of ordered pairs where you put in like a beginning and end point. However, this is undirected, and so 1, 2 in this graph is the same thing as 2, 1. Okay, so we might just recall that as we go through. So there's a 2, 3, a 3, 4, 4, 5. How many other edges are there? 3, 5. And 2, 5. Right? Good. And so now that I have my set V and my set E, I can say that the graph G is defined by the ordered pair VE. Okay, so this is the notation that you'll typically see. Okay, similarly, let's go ahead and get our directed graph. So here's an example of a directed graph, and in this case the ordered pairs are ordered pairs, they're not just unordered. So let's go ahead and draw 1, 1, 2, 3, 4. I'll try to make it look like the notes here. And so I could have an edge going this way, and then I could define an edge going that way. And so I would have 1, 2, 3, 4. Okay, and now our set of vertices, go ahead and write them down. So that is just 1, 2, 3, 4. And our set of edges. So go ahead and take a moment to write those down. Okay, so did we have 1, 2, 2, 4, 4, oops, gosh darn it, 3, 4, 3, and what else? 3, 4. Good. All right, so that is our set of edges, and we can define G by saying that G is this set of vertices with this set of defined edges. Very good. And so the book has a few other definitions. So let's call a chain a sequence of edges such that each edge shares exactly one vertex in common with the previous arc or previous edge. I should be consistent here, previous edge. Okay, so an example of a chain might be 1, 2, 1, 3, 2, 3, right? Because each pair here, the sequence of edges, shares exactly one vertex. So this shares the vertex 1, B's share the vertex 3. Good. And so what about the sequence 1, 2, 2, 1? Okay, that's not a chain. Okay, this is a chain. Good. All right. So a path is a kind of a chain, and those are the things we typically will deal with. So a path is kind of what you would think. It's it's a chain where the terminal node of the previous edge is the initial node of the next edge. Okay, so let's take another example here. Let's say 1, 2, and then the next edge would have to have the 2 in the front, right? Then we could put down a 3. The next edge would have to have a 3 first, right? So this is a path. An example of something that's not a path might be 1, 2, 1, 3, 2, 3, right? Is not a path. Good. All right. And so this really concludes section 8.1. However, there are some problems, some exercises in 8.2 that require us to convert word problems into graphs. And so let's take a look at a couple of those. We won't do all of them, but there's a couple of them that might need some explanation, so we'll go ahead and work on those. So the first one is the PowerCo example. PowerCo. And in the PowerCo, we have power is sent from node 1 to node 6. And so node 1 is called the initial node, of course. And node 6 would be our terminal node. Okay, and the other nodes are power stations. Substations, maybe we could say. Okay, and then there's costs for transmission between the substations. And so let's just go ahead and draw the graph, because it's really the easiest way to get this information. So we might have 2 and a 3 and a 4 and a 5 and a 6. Okay, and so I might have costs associated 4, 3, 2, 2, am I missing some? I'm missing a couple here. There's the 3, and this is 3. Good. And so a typical kind of question for PowerCo, maybe we want to start at 1 and get to 6, and we want to minimize our cost. So minimize cost to get from 1 to 6. Okay, and so the idea behind that is going to be the basis of an algorithm called Dijkstra's algorithm, and we're going to do that in the next video. But I just wanted to set up one more example before we do that. And it's kind of a nice example of where you might not expect a what do I want to say? A network or a graph to appear. So let's talk about this next one. I've only got about a minute, so I may have to. In fact, maybe I should pause here, and we'll talk about the other 2 examples in the notes, or at least one example in the notes, and then we'll get back to section 8.2 after that.